right? Hence, for the sake of convenience, since there are only two labels, let's keep that labels as either minus one or one. Right? So we can call them as either negative class or a positive class. Right? So let's say we want to build a classifier, which when given an example xi, it needs to correctly predict what the y could be. Should, should it be minus one or a plus one? And that classifier can be a function f of x. Right? F of x takes the input of xi and then gives us the number. And if the number is positive, then it is greater than or equal to 0. Then the predicted label can be considered as plus 1. And if it's less than 0, then the predicted label can be considered as minus 1. Right? Now, for the classification to be accurate, given a negative sample, it should give a value less than 0. And given a positive sample, it should give a value greater than or equal to 0. Right? So mathematically, you can write it as y into f of xi will be greater than 0. Right? Because if it's a positive sample, y will be positive and f of xi will obviously be greater than 0. So the product will be greater than 0. And if it's negative, then both of these values will be negative. So multiplying them will give a positive value. So that's how the classifier works. Right. Now let's come to the concept of separability. Now, given a data set, it is either linearly separable or not. Linearly separable means you can basically use a straight line or in a more mathematical terms, a hyperplane to separate the data points. Now, let's say these blue ones are negative sample and these red ones are positive sample. Right? Here you can perfectly draw a line to separate them. Even in this right case. Right? But if you look down here, you can't exactly draw a line which perfectly separates these two. Right? You either need to like sort of curve it a bit like this. Or in this case you need to draw a circular path. So linear matlab a straight line can't separate. Here you need a curved line or a non-linear line. Right? So these cases are not linearly separable cases. Okay. So let's first discuss about linear classifiers. As you know, since in a linear classification, all you need is a straight line. And this is a 2D case, by the way. Once it only uses x1 and x2. Or you can also use x and y axis, right? And for a straight line, you can basically write it in the form of f of x equals 0, right? And if the values are on the below, right, f of x will be less than 0. I think we studied this in JE and even in linear algebra. And if the point is above the line, f of x should be greater than 0. So that's the way. And okay, this simple line is also a linear classifier since it is separating these two points successfully. So we can basically represent it as a straight line equation, which is W transpose x plus B. Now this is basically a matrix form, right? Where W, X and W and X are both column vectors, while B is a constant, while W transpose X gives a dot product of it. Finally, a scalar, right? Now this straight line as a linear separator is basically a case for 2D plane, right? Now, what about 3D? When points are like three-dimensional points. In that case, to be linearly separable, you need a plane, right? And on even going towards higher dimensions, there are also like planes. And you can basically call them hyperplanes, right? In one dimension, hyperplane is a point. In 2D, hyperplane is a line. In 3D, the hyperplane is a plane. So basically, in a n-dimensional space, a hyperplane is a n minus one dimensional entity, right? Like this. But no matter what the dimensionality is, the equation of hyperplane is basically this. W transpose x plus b, right? So basically it's a plane equation. X1 into A plus X1, X2 into B plus X3 into C plus D. Remember the plane equation. This is the short form of it. Good. So again, let's say our data is perfectly linearly separable and we can draw a line. But still we have problem of what is the perfect line we can draw. Right? Now this line is obviously incorrect line. And let's say even if you draw a correct line, you can draw it like this, or even perfectly like this. How do you judge if a line is good or not? So one of the good metrics you can use is that you can basically take the distance. Right? Let's say this is the closest. Let's draw a line arbitrarily like this. Now let's say this point is the closest to the line. Let's draw perpendicular distance. And same with this perpendicular distance. Now this line you can consider it as a best separator when the line is as separated like as far as from both of the sets. Right. This distance A, let's call it A, and this is B. A and B should be maximum. Like it should be maximum at a maximum distance from both of the sets, both positive as well as negative samples. In that case, you can basically consider it good, like pretty well separated. Right. Now, this is the basic concept of HT. Now, if you see here, basically this is our point, hyperplane in a 2D space. And these are our, like, you can call it positive samples, let's say. And let's call the red ones negative samples for now. Negative samples because they are under the line. And substituting them in the line equation gives a negative value. Right. Now, if you observe, now this line is very well separated in a manner that the points which are closest to the line are equally separated, which means that the distance between them, or you can actually call it as a margin also, is equal. And another terminology we need to read is the points which are very closest to the margin are called as support vectors, which are circled here. And the margin is actually this distance, the distance between the support vectors in the perpendicular distance to the line. Right. Now, this line is said to be well separated when the margin is maximum. And when the margin is maximum, this distance is equivalent to this distance. So this line is perfectly in the middle of the both sets, both negative and as well as positive sample sets. Okay. So let's get back to geometry. Now let's say you have point x and you have a hyperplane with the equation f of w. Now the distance of the point x on the hyperplane you can write it as f of w of x by mod of w. Right, if you remember 2D geometry or even 3D. This was the equation. Now, given the hyperplane equation as W transpose X plus back is equal to 0. Here we didn't include that, but it can also be there. And W, as in the equation, is a perpendicular vector, as you can see here, perpendicular to the line's direction. Right? So that is this. So, what is the goal of the perfect boundary? The perfect boundary goal has to maximize the margin, right? This distance. Now, how do you actually signify this distance? Now, okay. Let's call that margin distance as gamma. So that margin is basically the minimum distance of the hyperplane to the point of its head, right? To the closest distance. So basically we'll check out the distances of all points, like distance from here to here, here to here, here to here, and then here to here. And the smallest distance which you can get out of that sample set is basically the margin, right? That is the closest distance you have to the set. So this is the equation for that, which is the minimum of I for all the samples xi and the distance from the hyperplane. So this is gamma by the way. And now since you got the margin, The goal is basically to maximize the margin, this distance. And this margin doesn't quite consider like positive samples and like negative samples. So for that, we also need to multiply it with the target variable, which is y, which is either plus 1 or minus 1. Right. Now, this this value can either be positive or negative, but this value is perfectly possible, given your margin is perfectly separating. Right. So this is the margin equation in the finally. This is the minimum distance of the point. Now, the objective is to maximize the margin, which means maximizing the minimum distance to a point, and that point can be in either cell. And since the equation of linear classifiers is basically W stands for vector plus T, so we'll substitute it here. So this is the final one. Right. Now, as you observe, we can actually scale the coefficients W and B by how much you want. Because when you scale, ultimately the objective function doesn't change much. You multiply W class with C and B with C. So again, both will cancel out. So basically it's unchanged numerically. So they can basically scale them as you wish. So for the mathematical convenience, let's assume yi into this W transfer xi plus B is 1. Right. Now xi star is the point closest to the hyperplane, which means it's a support vector for these points, basically. So considering that as minus 1, now for all other points, you'll automatically get the value of greater than equal to 1 because it's basically the distance, right? So in this case, when you consider this as 1 and substitute the 1 here, so you get the margin as 1 by W, mod W. This is the margin. So now we basically simplified it to maximizing just the modulus of W, the weight, not even the bias. Right. Now this is the objective function, whereas these are the constraints. Y like target variable into the substitution of the point, the linear classifier. Like the product of them should be greater than or equal to 1 for all lines, which means for all the points. Now, if this is not true, that means the classifier is not doing its work correctly. It's misclassifying some points. If y is greater than 1 and it is giving negative value, that means some point is on the other side of the plane than where it should have been. So since we're assuming they are perfectly linearly separable, so this condition has no exceptions. Right. So this is actually the ideal equation. Now, what we can do is we can basically apply KKT method and basically change the formulation of this from this to this. Right. Now here, what is the problem? The problem is that we need to optimize W so that we can reach the optimum solution. But instead of that, instead of W, if you're written in this form, in the form of Lagrange multipliers, and then you need to optimize, let's say, alpha here, alpha I, then it will be way more computational efficient and it will also help us further as we'll see. So here what we did is we basically wrote W as sigma of alpha y into xi, right? And then the linear classifier equation will become like this: sigma of alpha y into the inner product. Now this inner product is will not make our lives easier. Now the derivation of this is a bit complicated, so let's not delve into that for now, because the focus of the session is to get to the more practical aspects and intuition behind this SVMs. Right. So this is the like it is also called as dual formulation. And this product is highly useful for us later on. Now, obviously, the assumption we made till now is that the data is perfectly linearly separable. Right. Now comes the case where data is unseparable. Right. What about this point? Or this? Now, if you take this, here it's actually not a quite good linear classifier to draw a line in this way. because obviously this is the correct one, right? So there are some exception cases, and also like most of the real world cases now, the data sets are not much linearly separable. You need a curved line or a non-linear separator to separate the data set, right? So how do we deal with those cases? So there is one way. One way is allowing this type of exception. And the second way is basically projecting the data into higher dimensions, which we'll discuss later. So let's first discuss about this second approach. So what we'll do is basically we will add some slack variable, zeta r. Now let's understand it. Zeta is equal to maximum of 0, comma 1 minus the linear plus size prediction into the target variable. Now let's say the target variable is a positive. It's a positive sample. And the linear predictor also gives a positive value. So this entire value is positive, right? So as long as this value is between 0 and 1, it will be greater than 0. So that value will be taken by zeta I. And the moment this value is greater than 1, right, then this entire 1 minus this thing will become negative. And since that negative value is less than 0, so zeta I will become 0 only, right? And this is in the case of correct prediction. Now let's say it's misclassified. Let's say the target variable is -1 and it's predicted it as +1. So the entire this thing will be negative. So minus of minus will be positive. So this will be 1 plus a positive value. So this value will be greater than 1. So in this case, what I think is you can say that it's a violation, basically. So for a correct classification, it should ideally be 0. But sometimes, due to weak classifications, we can allow zeta value between 0 and 1. Right? And if zeta value is greater than 1, then you can confidently say that it's misclassified. And to geometrically get an intuition, let's take this value. Right? So for this value, the zeta is between, by the way, since it's below the limit, it's correctly classified. Right? But its value is between 0 and 1. Right? Which is basically the distance. See, we basically scale the values of W transpose in V to suit -1 and +1 as the support vectors. This is because of the assumption we took here, if you recall correctly. This sector scale. This is one at the support vectors. So the support vectors, this equation will amount to +1 and -1. And since it's also correctly classified, its value is between 0 and 1. So it's fine. But if you take less of this value, now it's obviously misclassified since it's way beyond this line. So if it's between, so it's obviously the zeta value will be greater than 1. And since it's also beyond the classifier, like the margin, so it will obviously be greater than 2 also. Right. So what we'll do is we'll basically calculate the zeta for all the like all these points. Right. Zeta will become 0 for all these points which are correctly classified and way beyond margin. And only for the values which are either misclassified or the values which are within the margin, the zeta doesn't have any value, positive value which is greater than 0. So we'll basically sum up all the values of zeta I and then multiply with the constant. You can basically call this here as analysis. So this is actually the equation we had before. We're just adding an extra parenthesis for this. So taking into account those points also. And we're modeling the linear constraint and instead of 1, we're writing it as 1 minus zeta. Right. For the correctly classified one, zeta is 0. So it's written as it is. And for the misclassified and not so good classified one, it will be greater than a value which is more than 1. So less than 1. So in these cases, we can basically call a regularization parameter. Right. अगर C ज़्यादा है, then the effect of zeta I on the entire function will be huge. So basically, you can't ignore the data. Right? So this will basically decrease the size of the margin so as to reduce the zeta or penalty. And if the C is very small, then the effect of zeta is on the general function is not so much. So while optimizing it, it doesn't decrease the margin as such. Marginality is price, the width of it. Right? So that's how you can give some leniency to your FCA. If you want to do perfectly hard margin, or hard margin must be perfect classification like this. You basically need to keep C as infinity or just a very high value like 1000, 10,000. It will suffice. And if you want it to be like this, which means have some leniency and just you leave it to some points. Then you need to set it to a good value, which is less than 1, practically. Okay. So this is how you get a bit control on how soft your margin needs to be. In this case, it's called as hard margin, so it's called as soft margin. Right. Let's see. Example. Let's have this case. Here you can see that all the these are mostly separated. There is one outlier point, which is probably due to noise. Right. Now, if you put C equal to infinity, which is hard margin, you will solve the line is drawn. And if you put C is 10, a soft margin, now it will basically allow this line to be misclassified, but this line is more or less good fit. Right? That's the point. Now, so there is actually a second way to do. Let's okay. So let's talk about how did this outer occur. So there are two reasons. Either that this is actually noise while recording the data, like due to the instrument error or something, some reason, this point actually shouldn't exist. But while recording the larger script here, right? In these kinds of cases, now, soft margin and hard margin concepts will work pretty good. But there are some cases where the data is inherently non-linear, not linearly separable, right? Like, let's say the data is like this. There are few points like this. They're forming a sort of circular shape. And let's say all the other data points are forming into circular shape, right? In this manner. So ideally in this type of nonlinear phase, the ideal margin would be circular, like this. But turns out that we can actually solve these kinds of problems also using HCM. Now this is called as Wesley Kernel theorem. Now to do this, you basically need to use this log sum instead of the previous one, which is this. Why? Because it will be computationally easier. Okay. So kernel trick में क्या होता है कि basically if you have data point like this, you'll basically extrapolate it to higher dimensions using some function, some transformation function, right? So what did it do? It basically increased the height of the points which are in the middle in a circular fashion and increase the height in a less magnitude or to a less magnitude. So points which are farther away from the center. So basically radius, right? So you can basically write it as a circular equation, which is like y equals x squared um, x squared plus x2 squared plus some constant c. So this is the circular equation, right? So for the points which are initially x1 and x2 in here, x1 comma x2, we're basically applying this equation and converting it into x1 H2, and Y. Right? Where Y is defined by this equation. Now, since x1 and x2 starts from the origin, these are starting from some point like say x1 dash and x2 dash. So ideally the equation will transform from x1 to minus x1 dash, like where x1 dash is a constant. But still the nature is still circular. Right. The same goes for x2. So it's basically x1 minus x1 dash and x2 minus x2 dash plus c. And when you apply this equation and then plot the data in 3D, you'll basically get this graph. And after you transform this data into third dimension, now you can basically use a hyperplane to linearly separate data. Right. So the concept here is that data is not linearly separable. Then you basically transform it using some suitable function like this to high dimension data, where it is linearly separable using hyperplane in third dimension. Right. So here again the question comes, how do you transform this? What kind of function do you use? Right. There are multiple functions you can use. They are called as kernel functions. So before we get into that, there is one thing we need to know. Right. Actually, now when you apply this, and since if the data set contemplates thousands of points, which is naturally the case in real world scenarios, then applying this transformation to each and every point is highly computationally inefficient. Right. So what you can do is to make it mathematically or computationally less intensive. There is actually a trick called kernel trick. So let's get back to this. This is a hard margin case without the slack variable, right? So let's say if you would have used this objective function, you would have manually had to, take all the variables or support vectors and then manually transform them using the equation that it can for database and then retrieve it and then apply this and then optimize it to get to so that's the case. Now this is in place. In alpha. No, right? Here is basically based on which is vector transpose and net, right? Now, if you observe the sector transpose into it, and if you wanna basically transform it to higher dimensional plane or space, so you actually don't need to do anything. You don't need to substitute the transformation here. What you can do is you can actually pre-calculate. Now, this is the linear case, which is the case which is already there. Where instead of x1, there is x1 and x2. So x dot y. So you can also call it as a linear kernel. If x1 transpose into x is just simple multiplication of dot product. And if you are transferring to the highest ranking space, let's say a 2D space, which is x, you can basically write that x into y as like this, in this form, right? So this is called as polynomial kernel. इसमें क्या होता है कि x dot y plus b again some constant a, b and d. These constants are again for our convenience only, so that we can change the importance of weights. So a dot x plus b is the correlating, and then we'll directly substitute this equation here. Now, if we actually mathematically extrapolate it, like extend everything and write everything, then directly applying the transformation to individual variables or taking this kernel function, they're mathematically the same. There is no difference. The difference comes in how the computer processes the information. Right. Doing it this way is computational way faster and easier, right? And there are lots and lots of kernel functions. You can also design your own. So this is also basically a polynomial kernel only, but its dimensionality is two, right? Here, although we omitted the x1, x2 point, which should have been there. So these are shortcuts to increase the dimensionality. If d is equal to 1, then this is just a linear kernel. A into x dot y, which is same as this with a bias term, and a equals to 1. Now if b is equal to 2, then you're increasing the dimensionality to third dimension, and so on. You can increase it, right? So that's how you increase the dimensionality. And the polynomial kernel से ये होता है कि थोड़ा और curved होता है lines, थोड़ा more complex होता है basically. And if you want say, okay, let's not decide the dimension. I just want like perfect fit, or you just lazy, which we all are to an extent. We can basically use RBF. This radial basis function kernel, its dimensionality is basically infinity. So how can you say it's infinity? It is infinite because this particular term is basically you can basically use multinomial theorem to expand it to summation of terms up to infinite dimensions. Sort of like Taylor series, right? So that's its dimensionality is infinity. But it's not get into the mathematical level. But somehow the thing which we need is that this radial based function kernel is quite good and actually this is the most used kernel, right? Because you can basically tune it to suit your sort of complexity so that it doesn't overfit or underfit. Let's get a like practical example. Let's see a visualization. So this is a good video by which we can see how kernels work in HCMS. So right, so what we saw here is similar one. Here is also actually the margin should be circular, right? So what we did is just like we extrapolated it, we also use a circular function to extrapolate the data is third dimension. And now it's basically linear separable by planes. So that's how basically kernels work, right? But still don't worry too much because lot of the content like to learn this mathematics stuff will be presented later, right? So this is how it is. If you want to basically use the RGS kernel, you can basically substitute into the loss function of the dual foundation instead of excess transfer into it. And even that, right? So that's how it is. So let's get to code. Let's see the practical implementation of it. Let's also the scikit-learn service. So let's import dataset from scikit-learn. One is the best class of dataset. Now for the dataset, let's print the feature names and the target name. So there are basically 30 features, if you can see, starting from mean variance, mean test set, mean perimeter, all are numerical features. So the dimensionality of this is basically 30, since it has 30 features. So like x1, x2 need then x30 to represent single point. And the label, since it's a binary classification, it's either malignant or benign. Right. Now, the shape of the data set is 569 cross 30, which means it has 569 rows or 569 data points. Means 30 columns with 30 features. And if you want to check like how are the features, you can basically use stats.data 0. So these are the 30 features. So all the values are between something like 0.1 to something like 50. Right. So for training, let's split the data set into train test case. So Scikit can also provide useful tools for this called as train test list. You can import it from the model selection part. So for the train test list, you give it the entire data, like the X part of the data or the feature, the target data. Or that's not target. And by the way, let's also print the target. So it's a binary classification as a 0 or a 1. Right? So the test size is 0.2, which means the test set should be 30% of the data set. And the random state should be in. So you basically divide it into same test case. Explain express baseline like that. Now the actual code to use HTML is actually quite small. Just two lines. You basically import it from SQL. Now, what we learned till now is the using of SVM as a classifier. It's called as support vector classifier. But with slight modifications, you can also use it for regression tasks. That was it's called a support vector regressor. Mm. And for the kernel, we can basically use a linear kernel, in which case all of these are not necessary. We can simply use this. Right. So let's first start with linear kernel. So first I'll declare it, and then I'm giving it the training data, external right now, so that it can fit the cluster. And then I'm predicting using chain of dots grading. First. So doing the prediction. So it's actually quite good. It has an accuracy of 96%, a precision of 98%, for 98, and a recall of 0.96. Right. So precision is basically for a positive sample, how many positive samples is it predicting correctly? So that is this precision. And so is recall. But recall and precision are like they're good to see, but even better metrics are F1 score generally. So its accuracy is actually quite good. Now oh by the way, let's fiddle a bit with C. Right. Let's say let's make it very hard and see how it goes. So the accuracy prediction and recall didn't change much, which means it's actually linear separable data in 30th dimensionality space. Let's make it really small, like zero point 0.1, and its default value is 1 by the way. It actually increased. This means data, like there are some sort of noise in the data set to which it should not show it. Like having a software magic improves the model. Accuracy will improve the precision and resolving. Right. Now, instead of a linear one, let's take a bit more complex one. This time, let's take RBS color. This is the popular one. So for this, I put C is equal to 1, And gamma is, let's say, 10. Right? So, by the way, what is gamma? So, it's in the RBS kernel equation. So, gamma is also part of this equation. Right? Yep. So, gamma is basically the constant here. If you can see clearly. Exponential of minus gamma into this modulus of exponential square. So, basically, if you increase the gamma, the complexity of model increases. Right? Because it gives more weightage to each and every point. And if you decrease gamma, then it becomes less complex. So gamma is a way of checking complexity. And gamma should be between 0 and 1, ideally. So gamma is, let's say, 0.999. The model is pretty bad because it's overfitting, right? The accuracy has been 63%, even the recall is 1. Individually, these values are not like good enough like, to decide the model. Apart from this, you also need accuracy as well as reference too. So even though this recall has been increased, the other also has been hampered. It's because of overfitting. Now let's decrease it. Now, one of the good ways to decide gamma is using this formula, right? This formula, what does it say? Make gamma equals to basically 1 by the number of switches in our data set, which are basically just 30, right? And the variance of X-ray. So what is the variance of X-ray? You can say it's 53,000, right? So if you basically calculate the entire formula, this is the value. 1.8 to 10 power minus 5 basically. So that's the ideal gamma value, like close to ideal. Let's put it. Right. So with this gamma value, it has increased very much. The accuracy is 94%, all the pressure is not that good, but okay. But result is 1. Right. Now we can actually fiddle with this value. Let's decrease it even more. Let's take it like, or let's increase it and see. Okay, now it's pretty good. Accuracy is 97, precision is 96, and recall is 99. Let's decrease it and see. Hmm. So the close value is somewhere between 10 power minus 4 and 10 power minus 5. Right. So in most of the cases, using RGF kernel and filling with the values of gamma and C is more than enough, usually. And this is how it's also used by the way. Now, apart from this, you can basically extend the functionality of SVMs for multiple tasks, like in NNP also for text classification, or in image classification also. And classify and other designs with the Java files or whatnot. And even object detection will basically make a sliding window throughout the image, and whenever human using the image, you'll basically use as a classifier. So that's basically object detection. Right. So that's how it is. And even now, for smaller data sets, SVM almost like always outperforms neural network if you tune it correctly. Like hyperparameters like John or C and all, are chosen correctly and you have normalized the data set. For larger data sets, however, it is better to use neural network. I said like here, we're optimizing W and here we're optimizing alpha. So how are we doing this? The method of optimization is usually called as gradient descent or some form of gradient descent. It can be deep gradient descent or it can be stochastic gradient descent or not. However, we'll talk about that more when we discuss neural networks. Then it will become easier. Right?